In this video, we will take a look at a new notation. Since Z is used with great frequency, we want a convenient notation to identify the necessary information. The convention that is used for a specific Z-score is Z of alpha. So here it is right here, pronounced Z of alpha. All right, so Z of alpha. It's not Z multiplied by a value. It is representing a particular Z, a Z that has alpha, which is an area under the curve, to its right. Let's take a look at an example. Visual interpretation of Z of alpha. Here we have a position for a Z-score. This particular Z has 0.05 to its right. So Z of 0.05 would represent a Z-score that has 0.05 to its right. We could find this by looking in table 3. Now, if it has 0.05 to its right, then it must have 1 minus 0.05 to its left, which is 0.95. So if we looked up 0.95 in table 3 and found the corresponding Z-score, we would have what that is equal to. Okay? Actually, I would be writing over here. And another example would be Z of 0.9. This is representing a Z-score that has 0.9 to its right. So I challenge you, before that's drawn on there, to draw a diagram similar to this one and shade the area that represents this and mark where that Z would be. Pause the video and give that a try. Okay, so now that you've had a chance to try that, here's what it would look like. You've got 0.9 to the right of a given particular Z-score. If 0.9 is to the right, then 1 minus 0.9 must be to the left. So we have 0.1. So in order to find that Z-score, I could go to table 3 and look up 0.1 and find the Z that is closest to that. Okay, so getting back to that first example, Z of 0.05. Remember, it's got 0.05 to its right, therefore it's got 0.95 to its left. And notice I'm putting those with 4 decimal places because in table 3 they use 4 decimal places. So let's take a look at looking up 0.9500. When you look that up in table 3, you will notice that looking through to find the values closest to 0.9500, it doesn't actually exist. You have 0.9495 and you have 0.9505. Notice that both of those are the same distance away from 0.9500. One is 0.0005 lower and one is 0.0005 greater. So when this happens and they're at this exact even split, use the most extreme value. We say, sometimes you might say the higher, but if you're in the negative, you want to go to the more negative. So instead of choosing 1.64, we will use 1.65 because that's the most extreme, okay? And therefore, we know for sure that we've covered 0.9500. This one is just a bit in the low end. So therefore, Z of 0.05 is equal to 1.65. This means that the Z-score that has 0.05 to its right is 1.65. Okay? Here's a practice. You can find Z of 0.95. I encourage you to draw a diagram to represent where this Z would be, and that will look like this. If it has 0.95 to its right, it's got almost everything to its right. So the whole right side over here is shaded. This is 0.95. That means that to the left is 0.05. And so if we look through table 3, we will find that the z-score that has 0.05 to its left is minus 1.65. And we may have seen that earlier because of the symmetry of the normal distribution. Before, we just looked at the right-hand side. This is just like looking at the same, except the 0.95 and the 0.05 are reversed. Okay, so there are a couple of diagrams and I encourage you to be able to draw these diagrams and understand the correct area to shade. So Z of alpha, just to repeat, the alpha is the area to the right of a particular Z. And this will be equal to whatever the Z is. Okay, here's a practice for you. Pause the video and find Z of 0.90. I've done the diagram for you. You find the proper Z score to match Z of 0.90. So now that you've had a chance to find it, and you would have paused the video, let's see what the answer gives. We take a look through table 3, and we are looking for 0.01 because table 3 gives us the cumulative area to the left of a given value. So that becomes, the closest will be minus 1.28. So Z of 0.90 is equal to minus 1.28. Okay, so those values can be found from table 3. However, table 4 has critical values of the standard normal distribution for us, and it has values that are most commonly used. So instead of having to scan through all of table 3, for the very commonly used ones, you can find them more directly from table 4. So in first part of table 4, part A refers to the one-tailed solutions. And a one-tail looks like this. We either have a right tail or a left tail. And because of the symmetry, you are probably only going to be given the right tail in table 4, and you'll just put a negative in front for the left tails. This is an excerpt from table 4. So what it tells us is that for an alpha given on the top row, the corresponding Z of alpha is below. So this means, if I look at this particular example, that if alpha equals 0.05, Z of 0.05 equals 1.65. All right, so Z of 0.1 equals 1.28. Z of 0.025 equals 1.96. So those are commonly used Z of alpha values, and they are in table 4A. Now, if you need them for the negative side, the left tail, you just put the negative in front. Keeping in mind that the alpha value is always area to the right. I encourage you to have a look at table 4. Let's look at an example determining z-scores for bounded areas. Z-scores can also be determined for bounded areas of the normal distribution. We can find the z-scores that bound the middle 95 or middle 0.95 of the normal distribution. Given 0.95 as the area in the middle, the two tails must contain a total of 0.05, right? Because these two add up to 1. So what does that look like in a diagram? Each tail will contain half of 0.05. So the middle, this is in the middle 95%. The tails, in a sense, contain the other 5. Or evenly split 2.5% or 0.025. So that's what bounded areas are used for. And this is these are found in table 4B. You'll notice in table 4B, two-tailed, right? So two tails are for bounded situations. You are given the alpha value, or if you know the alpha value, you can find the z of alpha over 2. 1 minus alpha will be the area in the center, like the 0.95, right? So 1 minus alpha is the area in the center. Alpha equals the total value of the two tails. Alpha over 2 is the area in only one tail. Determining z-scores for bounded areas. From table 4B, we find z of 0.05 over 2, which is equal to z of 0.025, to be equal to 1.96. Using the symmetry property of the distribution, we find that z of 0.975 is the negative of z of 0.025, which is negative 1.96. Therefore, the middle 95 of the normal distribution is bound by minus 1.96 and positive 1.96. Almost 2. And this is where the empirical rule tells us that 95% of the data lie within 2 standard deviations. It's actually minus 1.96. And the empirical rule is a little bit of a generalization. Right, okay, approximately within 2 z-scores of the mean. Okay. So now that we have finished talking about z of alpha values, I encourage you to do the practice, and hopefully that goes well for you.